Okay, hello everybody. We start today final chapter of for our course on statistical physics. Basically, it's going to be about interactions. So, if you look what we have succeeded in doing so far, so we introduced the mechanism. We introduced some specific laws, the thermodynamics laws, the first and the second. We used it extensively in order to define ensembles, define the statistics of different ensembles, apply to systems where the energy was fluctuating, the number of particles were fluctuating. And we have a big tool, big machine, in order to actually obtain the equation of state starting from the microscopical description. And we have done it successfully for several quite sophisticated models. So not the two-state models, but the bimodal was actually something big. The lead battery radiation. Afterwards, we have done successfully it for the Fermi fluid. All of those examples, they're working quite well in reality, so we can very well approximate a lot of situations when the radiation of the light can be described as a black body radiation. The vibration of the solid for the high temperatures and the low temperatures is also very well described by the Debye model. Fermi fluid, describing very well a lot of systems, a lot of metallic systems and their thermodynamic properties. Now, what is common in all of those examples that I just mentioned? Eventually, everything was some sort of a gas. Even though we started with something very complex like a Debye model, eventually we managed to come into and obtain a situation when our particles were non-interacting particles. Like, for example, the Einstein model, the original Einstein model. The particles were non-interacting. They couldn't care less about what the energies of the other particles are. Each had some specific effective frequency. It was vibrating with it, and that's it. The same was for the black body radiation. There was some interests about what is the distribution of the energies, but nothing was interacting. The same goes for the Debye model. We all started with something that interacts with each other. We had our Hamiltonian, but eventually we managed to write it down as a sum of a lot of harmonic springs, right? Non-interacting harmonic springs. There was some specifics about the quantum statistics and the specifics of the distribution of the energies. But the particles themselves were completely non-interacting. And this is what we have done so far. Now, the question is why? Why we only managed to do something about non-interacting system? The true answer is because it's very, very hard to do something where there is a lot of interactions, right? So think about mechanics, regular mechanics, that solved even analytical mechanics or regular Newtonian physics. We basically solve problems with one particle, two particles, and that's it. No more particles. Three particles. So this we know, this we know. Three particles. And well, for some very, very symmetric situation, when you have those three particles, you know what to do. In general, we don't really know how to solve it. We know how to solve two particles because eventually we can transform this problem into one particle. So we know how to do something where the system is non-interacting because we know how to treat single particles. We don't really know how to treat interactions between particles. You can say, well, we had a solid body. Right? In mechanics, there was a lot of particles in it. rotation of a symmetric or asymmetric top. But eventually we treated the symmetric or asymmetric top as a one single particle that had effective interactions inside and effective interactions with the gravitational field, electric field, whatever. There was always the problem that we have solved so far is about what happens to a single particle in a field, what happens to two particles in a field, and then eventually we go from two particles to one. We haven't done three particles, four particles. Statistical mechanics claim to say, well, we don't know how to do anything with three particles. We know how to treat a huge system of thousands and millions and billions of particles. And what we have managed to do so far is actually to treat non-interacting particles. So again, although we are treating huge systems, but they are non-interacting, and this is why we can solve it. But all the systems that we have in nature, we see that there are strong interactions. Very strong interaction, I would say. Sometimes those interactions can be transformed into something effective. For example, the board, eventually I can transform it for some specific cases as a big single particle and only treated center of mass. For vibrations, I also can maybe transform it, again, under some specific circumstances, into a system of non-interacting phonons. And my question would be, well, can I do something about interactions? Can I invent a form that I can treat interactions in such a way that eventually I will transform everything to a non-interacting picture? We will try to use a specific example of magnetic systems where interactions present and the particles are very, very, very strongly interacting with each other. We'd like to see and to use this as an example to explain to you how interactions enter into statistical physics and what are the tools that we right now have in order to solve the problem. Not to get rid of them. It's not that you can always neglect them. Sometimes it's true that you can say, well, the system is non-interacting. Sometimes you need to take them into account and it works to a specific level that's called mean field. And sometimes you don't have a choice but actually to treat them right. And in the two lectures that we have left, this is what we will try to attempt and perform. In quantum statistics, we observed Fermi statistics, we observed Bose statistics, a little bit neglected the Bose condensation phenomena. I told you about it, but I haven't specifically treated on the board. But I think it's much more important to treat interactions and to describe to you what happens in an interacting systems instead of doing, again, from developing some lengthy integrals about Bose condensation. Okay, so we are starting with magnetic systems. Why magnetic systems? Well, because there are several very interesting phenomena that are associated with the behavior of a magnetic system. So, first of all, and this phenomena was already described before any understanding of the quantum nature of our world. So, if you look on a system, in classical prescription, we can understand that it's divided into a lot of smaller parts, okay? And those small parts have some specific magnetization, intrinsic magnetization that is associated with each part, okay? And the arrow is, well, it can be the description or it can be the direction of the inner intrinsic magnetic field or magnetization that is associated with this small region of the material. So this is the classical description. A lot of small particles or small regions, but each of them has its own intrinsic direction. And in general, those intrinsic magnetizations, okay, can actually show any direction whatsoever. Okay. What we know is that the energy of the system, if it's dependent on the magnetization, self-magnetization of the system, dot the external magnetic field that we apply to the system. Right? This is what we know. And this is already classical electrodynamics. You have a self-magnetization, you have a magnetic field, and then you have an energy. Right? Now, in quantum physics, we understand a little bit more, much more, about the magnetization properties. The magnetization properties are associated with the free charges that we have in the system. So, there is a material, and there are free charges, which actually are the not completely populated cores of each atom or molecule. And those electrons have specific spin. And those spins are the magnetic properties of these particles. So when we are looking on some specific magnetization in the system, it would be the magnetization that associated with each atom is sitting over here. And the magnetization of each atom is dependent on how many electrons or free electrons it has in its upper core, quantum core. Okay? So we know the intrinsic, non-intrinsic by microscopic behavior of each magnetization. It's basically what happens to those free electrons, unpopulated cores. But the energies should be exactly the same. So the only big difference for us is that in classical physics we would say, well, there is some specific magnetization that associated with the material. We would say, well, we know where this magnetization is actually coming from. It's coming from the spins of the magnetic spins of the charges. Great. Now you see over here that it's a dot, mu dot h. So the magnetization is dependent, the energy is dependent on the magnetization and the external field, but the directions of each of the intrinsic magnetic spins, I would say, is also dependent on the field. So in general, I would say the spin can actually show any direction whatsoever. Those small vectors over here, okay, they're randomly distributed. Take, for example, one single spin. It depends on the electron, on the charges, and it can show this direction, that direction, and in general changes its directions. We know that Sz is actually fluctuating. It can have specific values, the spin of an electron or the spin of the atom. It can have specific values, but it can change its values as a function of time, okay? Because it's going to be in all of its possible eigenstates. Now, if we apply a magnetic field, external magnetic field, what happens is that each of those spins, each of those magnetic spins, will prefer to follow the direction of the external field. Okay? So if the field is going up, all the spins in the system, all the spins of the system would prefer to actually follow the direction of the external field. Okay? And this is how we obtain magnetization. So we can have a material, and it's called the paramagnetic material. When the magnetization of the magnetization, let's call it M, the magnetization of all the spins together, okay, the magnetization would be 0 if H external equals 0, and something non-zero, let's call it non-zero, if the external field is also non-zero. Okay, so if we have an external field, the particles, the single spins, would try to follow it. Okay, there is a preference for the single spin magnetization direction, and we obtain that we have a total magnetization. What do I mean by total magnetization? So we can look on the magnetization of a specific part of our material or a specific charge, okay, or atom, and we'll call it mu multiplied by S. Okay, when the S is what? The S is the spin of this specific part. Okay, mu is generally the Bohr magneton, and the S itself can be, well, depending on what the particle we're looking upon. Right? Now, if this is the magnetization of one specific particle, the total magnetization M is sum of I mu Si. And, well, the paramagnetic material states that if there is no external magnetic field, the total magnetization is 0. How come it happens that, well, we sum up over a lot of different particles, a lot of different spins, and in total we are getting 0? It basically says that all of those are, not that everybody is 0, but they are randomly distributed. Okay, so some of them are in this direction, some of them in that direction, some of them follow different direction. So there is a complete randomness inside the system. And if we sum over all different directions of the particles, what we obtain is that the total magnetization is 0. Okay. Now, what happens if we turn up the external field? Then immediately each of those spins will try and follow the direction of the external field. Right? So if we have H in this direction, what will happen to the internal spins? Well, they all will try and follow, in general, this direction, external direction. And then we obtain a total magnetization. So this is the big difference in the paramagnetic material. No preferred direction or some specific preferred direction. Okay? And it always will depend on, well, what is the external field that we have in our system. So this is very clear, and this is, we can understand this. We don't go into the quantum mechanics in order to describe what exactly happens to each of the spins, etc., etc., etc. But the interpretation is clear. There is some interaction between the external field and the intrinsic spin, and then the spin tries to follow the direction of the external field. Now, but there are some other materials that we call ferromagnetic, and ferromagnetic materials, they actually perform something which looks a little bit of unnatural to us. What I mean by, so ferromagnetic material is a material that has, it's a macroscopic material that has an net magnetization which is not 0. So we'll say, well, yeah, we can actually understand this because, well, we can understand that there might be a situation that we somehow quenched everything in a system, right? And all those charges are directed into a specific, or they're sitting in the material such that there is no net general randomness, but there is some sort of an order inside. So maybe they are somehow sitting in such a way that there is enough spins that follow a specific direction even without a presence of external field. But if we plot the net magnetization So this is as a function of temperature. This is m. What we would see that there exists a specific critical point. It's called Tc, Curie temperature. And this Curie temperature is stating the following. For temperatures that are above Tc, the net magnetization is 0. For temperatures below Tc, the net magnetization, let's forget about the absolute value, it can be something which is non-zero. And it goes like this. And interestingly enough, sometimes it can actually be negative. So there is a bifurcation point. You see there are two solutions. The magnetization can be below a specific temperature, which is dependent on the material. Okay? There is a solution when the total magnetization is positive, and there are situations when the total magnetization is negative. Now, what do I mean by this? I mean that I can have a material that behaving as a pure paramagnetic material for high enough temperatures. Okay, for high enough temperatures higher than Tc, it cool down the system. Then this material that was completely non-magnetic will become a magnetic material for low temperatures. Okay, you can take a magnet, heat it up. Well, the Tc of a real magnet is very, very high, but they are still there. You will heat it up, it will lose its magnetization completely, then cool it down, and then some sort of a spontaneous magnetization will appear. Why spontaneous? Because what we believe that happens there, that if there is no order in the system, and we do not apply any external field, we do not expect any magnetization whatsoever. What happens here is that for H equals 0, the system has a magnetization, and this magnetization shifts and changes as a function of temperature, and it's a spontaneous magnetization. Why spontaneous? Because we can start from high enough temperature, then there would be completely no order whatsoever in the system, completely no magnetization, so this is the case, and we will eventually go to this case, not by applying an external field. If we apply external field, this is clear what happens. There is some specific direction, preferred direction, but this situation will occur also only by changing the temperature. So it's not that we are changing the interaction strength. What we're changing the temperature, and then spontaneous situation that looks like this appears. Now, what I mean by spontaneous and what I mean by non-zero magnetization. So, if you plot a graph, and we look on the magnetization of the material as a function of time. So this is the magnetization. And we have H equals 0. A paramagnetic material will have some fluctuations, but those fluctuations are small and they will sit around 0. Right? This is what would happen for paramagnetic material. What happens to a magnetic material? H equals 0, and it has a spontaneous fluctuations. It also has some small fluctuations, okay? But those small fluctuations sit around a non-zero value. And the magnetization, it fluctuates as a function of time. When I'm saying it has non-zero fluctuation, I'm not saying that, well, this small wrinkle over here is non-zero. No. What I'm saying, it has a big macroscopic value. But there are some small fluctuations around it. But it has big macroscopic value. This is why I can plot the average M. Okay, so here the average M is greater than 0. Here the average M equals exactly 0. Now, when I'm saying there are two solutions, how could it be? How could it be that the system actually can be in a positive magnetization or negative magnetization? Well, the thing is that sometimes very, very, very rare event can occur that can take me from this magnetization to this magnetization. Okay. So the probability that you would see something like this is very, very, very small. But in theory, what might happen that sometimes you would see transitions of this sort. And if you're in M greater than 0 or M smaller than 0, average M smaller than 0, oh, it depends on the history and depends where you started in your disordered phase, but you actually can observe this solution and you can observe this solution, and very, very, very rarely you can observe transitions. In simulations you can actually see them, you can bias your system toward this. So this is a ferromagnetic situation, and it shrinks down, both those solutions shrink down to one single solution of M equals 0, where? At Tc. And the transition is not exactly smooth because I have plotted here something that actually decays as a parallel. Okay, so, and we will see, maybe not today, maybe next week, the transition is, it's a phase transition that happens here. System changes pretty abruptly from being a ferromagnetic to paramagnetic. So what do we see here? We see here spontaneous magnetization. And the interesting part, specific this part, when we had 0 transition and then magnetization occurs, this is also called in physics spontaneous symmetry breaking. Symmetry breaking. Why I'm calling it, not me, but whoever called it, as spontaneous symmetry breaking, because, well, look at this picture. When the particles are disoriented, the spins are disoriented, and each can follow whatever direction that it likes. So the total symmetry, I don't care where there is a total symmetry in the system, because the particle can follow this direction, or this direction, or this direction, or that direction. It doesn't care. Everything is very, very, very much symmetric. Okay, so then we call there is a very big symmetry in the system. And now the symmetry was broken. What do I mean by broken? There is a preferred direction that everybody, or at least big chunk of the material, prefers to be there. Okay? Something has broken this total symmetry when you don't care where to go. What is your preferred direction? I don't have a preferred direction. I can be there or there. Now I have a preferred direction. Well, there. I can for some time be here, but I always prefer to sit in the exact direction. Now, if there is external magnetic field, it is clear we have broken it, externally broken it. And it's completely not clear what happened that we have broken this symmetry by only changing the temperature. Okay, so it's trivial to break a symmetry by saying, well, you should all go in there. Now I'm saying you should all go there without actually saying what is there and only changing temperature. Now, how this situation occurs? Because we can say, well, they don't care about each other. Now they care about each other because there is external field. They don't care about each other too. They care only about the external field. This is why they want to follow there. Okay? But since the situation occurs even without the external field, what we can conclude is that there are some interactions between the different spins. And as we lower the temperatures, those interactions become more and more important. And in some sense, for temperatures that are lower than Tc, the interactions become dominant. They overcome this energetic fluctuations, free gas fluctuations, kinetic energy, etc., etc. And they create this general order. This is a disordered system, and this is an ordered system. What created an order? Interactions between different particles. Okay? We know how to solve and how to treat those guys. Okay? We don't really know how to solve this equation and how to treat it. And we don't really know how to go from this picture to this picture. Why? Because all we have done so far was for free particles. And now we have a lot of systems, the magnetic system is only one of them, that have this transition, this critical transition from paramagnetic, here we can do something, we absolutely don't know how to do something, and even more, we don't really know how to transit from this situation into this situation. Okay. And there is a lot of interesting stuff going there. This spontaneous symmetry breaking, etc., etc. Now, additional example why it's interesting, maybe you have heard about it, it's hysteresis loops. So, for a paramagnetic material, so all of this is statics. Okay? Eventually I'm looking on the average magnetization and everything in statics. But I can also do some dynamical explorations. Okay? So I can measure M as a function of H. Okay? And I'm saying I'm in a paramagnetic phase. What happens here? I'm starting from H equals 0, magnetization is 0. Or I'm starting from low enough, negative external magnetic field, the magnetization will rise, okay? It will go from 0 and it will do something other afterwards. Okay? So if I'm increasing my magnetic field, my external magnetic field, the magnetization will grow and grow, etc. It will grow. If I'm going in the opposite direction, so I'm starting from a large external magnetic field, magnetization will be large, and as I'm decreasing my external magnetic field, the magnetization will decrease also. Okay? But I will always follow one single curve. I'm going up, I'm going in this direction. I'm going down, I'm going in the other direction. Now for ferromagnetic material, or in this ferromagnetic phase, something else happens. Okay? So this is again M, this is H, and this is ferromagnetic. I'm starting again from this, from the small h or negative h region. I'm growing. And I'm not crossing m equals 0. Why I'm not crossing m equals 0? Because I know that even when h is 0, I'm in a ferromagnetic phase, I will have some spontaneous magnetization. Why it's negative? Well, because I'm started from a situation that everything was negative, So the system will prefer the solution of a negative magnetization. I will increase my external field more and more and more. Eventually the magnetization will climb up and go separate somehow. Okay, so this is going in this direction of increasing the external magnetic field. What happens if I'm now starting from here, okay, and I'm decreasing my magnetic field? Okay. So first, I would see exactly the same behavior as I've seen here. I'm going in the opposite direction on the same curve. But something interesting will start to happen. Because eventually, I will get separated from the going up curve, and my going down curve would cross the magnetization at a positive place. So here the external field is 0. I still have a net magnetization. It is positive. Why? Because I'm now choosing this solution. Okay? I'm starting from a phase where I was ordered, so the system would prefer to stay in this solution. I would increase my net magnetization more and more and more. Eventually it will go 0, and go like this. Okay? So you see, this phenomena is called the hysteresis loop. Well, basically, going in one direction gives me one solution, this one. Going in the second direction gives me the upper solution, and there is a big difference between them. Okay? There is a big difference between them. Now, again, this is something interesting. I expect the system, this is my external parameter, H. I'm expecting my system to behave that would be only one solution for the magnetization, for the value of the magnetization per system for given H. What I'm getting that I will have two solutions. Here I will have either negative or either positive magnetization, and it will depend on how I got there. So up to now we always said, well, there is an equilibrium, and this equilibrium depends on the internal parameters and on the external parameters. You have external parameters, you should define them, and then there is only one solution for the equilibrium. What happens here, we see there are two solutions. Not only one, but actually two. And it depends on how I got to this value. I can be at negative H, okay, minus H0, and magnetization could be positive or negative. All the way in this hysteresis loop. Okay? So those interactions that they create something that I haven't anticipated so far. Because all my thermodynamics was based on the assumption that there is a state function, and this state function uniquely defines the state of the system. Here, the state of the system is not uniquely defined. Right? So you see that cool and interesting physics appears here that we have to resolve somehow. And what I claim is that all of this physics is due to the interactions that are actually very important and very, very, very interesting. Okay. So what we are going to do now is to try and analyze the effect of these interactions.
Well, so there's a possibility that it will, well, firstly negative and then suddenly jump to positive, just like.
Okay, so you're saying, well, you brought it here. Here you always ramp up the magnetic field. So you're going with H and you're increasing it constantly. So this is a dynamical experiment. But you're saying the following. So I brought it here, okay? It will sit here, and eventually it will jump into this position. Yeah, it could happen. It might be very, very, very rare. But it can also jump backwards afterwards.
Yeah.
Okay, so what I brought it over here, those events that it sits in one place and then it goes to another solution. So it basically goes from here to here. This could happen, but it can also have the other way around. But those transitions are extremely rare. They're very, 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 very rare. So what I taught you about equilibrium, you say, well, you sit there and eventually you will reach equilibrium. The thing is that the waiting time, so the time that you will have to sit and wait for this specific transition, can be larger than the age of the universe. Okay? So sometimes you say it should happen. When? Well, not during my PhD or my advisor's PhD and not my grandfather's PhD. So it's not happening. In theory it might. In simulation it might, when you bias it and build it properly. But if you have a some magnetic field and you're saying, well, this magnet will jump from point in z direction to point into the minus z direction. And I'm now going to wait. Take you a while. Okay. For our reasons, it's just two solutions, which is absurd a little bit. But in mathematical theory of bifurcations, it can happen. It can happen that your function will have two solutions. It's interesting. And this exact point is called a bifurcation. There's a lot of mathematical theory around it. Hop bifurcation, etc. It's connected to nonlinear dynamics. Okay. So we are in a situation that we have observations that are really interesting. We cannot really understand them based on whatever me or everybody else taught you so far. Okay? But at least we can, we can try. We have our big machine of statistical physics. And so this is our tool, and this is what we are going to use in order to appreciate what are the circumstances and what is the physics that is responsible for all of this. Because this is interesting. This is counterintuitive. So what do we do when we have a problem in statistical physics? We always start from the partition function. And the partition function in general, for example, for the canonical ensemble, it always looks the same, right? It's a sum of I, e to the minus beta ei. It's always the same. It's like Richard Feynman states, this is the top of the mountain. Now you only have to specify all the details. But this is the last formula. Okay, now what are the details? The details are what are your EIs are and what are the I's. Okay, so what is the different energies that you are assuming that your system is having, and what are the different states for this energy. Now, where those EIs are actually came from. Okay? Now, let's look on this value as an observable of a quantum operator, quantum Hamiltonian. Okay, so if we have e to the minus beta Hamiltonian that is acting on a state I. What is the state I? Is the eigenstate of the Hamiltonian. Right? Now, if we use the bracket, have you learned bracket notation? Yeah? Okay. So if we use the bracket notation, we know that the e to the minus beta h operating on I will give us something. Now, what is this something? This something is, so if the Hamiltonian is operating on I, so it's bracket of I, okay, the answer here is what? Is simply EI. So the eigenvalue of the Hamiltonian that is associated with state I. Now, if I have a function that is e to the power x, so the Taylor expansion of this function is what? Is 1 plus x plus 1/2 of x squared, etc., 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 right? Now, using this formula, I can say if I have e to what power? E to the power of some operator. It can be Hamiltonian or non-Hamiltonian, I don't really care. What I actually mean by writing an exponent of a Hamiltonian, I mean that if I expanded in a Taylor sum, it would look like E1 or operator of I1 plus Hamiltonian plus 1/2 Hamiltonian and Hamiltonian, etc., 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 etc. Okay? So this is the usual expansion. When I'm saying I have an exponent of an Hamiltonian, I basically say that I have this polynomial representation of this operator. It's just a lot of operations or multiplications of Hamiltonian by Hamiltonian. And this is easy, I know how to do it. Okay? So from this description, if I have e to the minus, so if now I am applying a bracket to the Hamiltonian, so if I have I, and I will have I, okay, what it will be? It will be that I'm applying the same bracket, I, to the expansion, 1 plus Hamiltonian plus 1/2 Hamiltonian and Hamiltonian, etc., etc., etc. And I will have I over here. Okay, now where this leaves me? So if I have a Hamiltonian applying on a bracket, gives me EI. If I have a Hamiltonian applying on a Hamiltonian on a bracket, it gives me I Hamiltonian applying on EI ket I, which also gives me EI bracket of Hamiltonian EI, which equals to EI squared. Okay? This is the application of the bracket of Hamiltonian and Hamiltonian. Okay? And I don't have to worry here too much about the commutative problem. Okay, so this guy is going to transform into 1 plus EI plus 1/2 EI squared, etc., 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 etc. Okay. So the eigenvalues of e to the Hamiltonian basically goes to what? E to the power of EI. Because this is an expansion, the Taylor expansion of e to the power of EI. Okay? So by doing this and remembering what I mean by e to the power of Hamiltonian, that's basically, it's simply an operator, I know that e to the minus beta Hamiltonian I bracket I equals to e to the power of minus beta EI. Okay. Then the sum, or z, which is the sum of I, e to the minus beta EI, okay, goes to sum of I, bracket I, e to the minus beta Hamiltonian, ket I. Okay. And this guy equals exactly, so e to the minus beta Hamiltonian is an operator taking the eigenvalues of operator, but only the i's. Think about it as a matrix. So what I have over here, it's a trace of the matrix, right? I'm only taking the values on the diagonal, right? I'm taking 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc., etc., etc. I'm not taking the bracket of eigenstate 3 and eigenstate 4. This is not part of my sum. This guy is called a trace of an operator, like a trace of a matrix, right? The summation over the diagonal parts. So Z equals a trace over e to the minus beta Hamiltonian. Okay. We haven't used this description so far, but when I basically say that it's a trace of e to the minus beta h, I'm saying I have to take the summation over all eigenstates of the Hamiltonian. Okay? So for each problem in statistical physics, in order to find what is the partition function z, right, I need to define my Hamiltonian, I need to define its eigenstates, and then I need to take the trace over all the eigenstates of this Hamiltonian, or not the Hamiltonian itself, the exponent of minus beta Hamiltonian. Now think about this problem, which is quantum mechanical problem in theory. I have a material, I have a lot of spins, magnetic systems, electrons, whatever, yes, inside over there. And now I need to take the Hamiltonian and trace it. The Hamiltonian is huge, it's enormous because it's a macroscopic system, it includes everything. Okay? You're spending huge amount of time in your class on quantum mechanics to solve the, what atom you're solving right now. So you're saying you're solving an atom with what? With 1 electron. Think about solving the same problem with 3 electrons, 4 electrons, okay, or 3 atoms. The Hamiltonian is enormous. It's impossible even to write it. Okay, well, you can approximate it like Hartree-Fock approximation, etc. But you need to approximate somehow your Hamiltonian, and then to take a trace. It's an impossible problem. So even before the summation, doing something with this in reality is impossible. So what we are doing in physics? In physics, we always have this problem. The life is complicated. What we are doing? We're writing some sort of approximation. So we don't know what is the true Hamiltonian of the system. And we actually don't care. What we care about? We care about the physics. This physics, the spontaneous magnetization. So we need to write some sort of a Hamiltonian that approximates, for our needs, what is happening inside the system, and then we'll study it. Sometimes it's insufficient because we actually do not catch the physics. Right, the Einstein model, right? The Einstein model is not catching the physics of low temperature vibrations because it neglects them. It neglects the interactions between different particles inside the material. Okay? But it's a good model for high temperatures. So what we need to do, would have been done like 80, 90 years ago, is to take this guy and to try and approximate it, not this Hamiltonian, but write an effective Hamiltonian for a system and study it. It's called a toy modeling. We cannot solve everything, but we can invent some sort of a toy that will describe our system. More specifically, it will describe specific parts and behaviors of the system, and by studying this toy model, we can understand something about the physics, very, very, very strange and hard physics that happens in the true material. So what we are doing right now is actually going into a very famous model in statistical physics, or in physics in general, that will describe to us what is happening inside the system, at least partially. So the model that we are going to use in order to describe somehow the magnetic properties and the magnetization behavior is called the Ising model. Now there is a rule of thumb in physics. When you have a law or you have a model that is named after someone, usually that someone have never invented it. In case of an Ising model, it was invented by William Lenz, sorry, W. Lenz, approximately 1920. He gave this model to his student, Ernst Ising, that published together with Lenz the solution, one-dimensional solution of this model, and around, so it's 1D, around 1925. And the solution was wrong, and there's a lot of problems with that. But this model became popular because you can play with this, as we see. You can understand something, and you can give predictions, and you can actually study and develop a physical feeling and a physical description of the magnetism, and more importantly, properties of interactions and how they actually enter your system. A fantastic solution of this model, it was ingenious simply, was performed by Lars Onsager in 1944. This is 2D, two-dimensional system. In a second I will define what the model is. So Lars Onsager solved the Ising model for magnetization in 2 dimensions. Nobody knows how to solve this model in 3D. Nobody knows how to solve it in 2D with a field. It's a very, very hard problem, although the model itself is very, very, very easy. Now it's hard because interactions are actually very, very hard. More afterwards, this model facilitated the study of disordered system, the study of transitions from order to disorder, not only for magnetization, but actually for other systems as well. Model for phase transitions. Eventually it leaded such people like Michael Fischel and Cyril Domp. Cyril Domp was sitting in this building up in the corridor, and Leo Kadanoff to actually develop something which is called Normalization Group, which is an approach, the most general approach that we now familiar with towards interactions. Eventually, Ken Wilson got a Nobel Prize in 1983 for the Normalization Group. And basically, this model facilitated maybe everything that we now somehow understand about interactions, not only in magnetic systems, but every other system, physical system as well. So what is this model? It's extremely, extremely simple. So now we only care, in general, if we take a particle, the spin, you can say the spin, it's an arrow that can point in any direction. Okay? Now we only care about the z direction of the spin. We are looking on the z projection of the spin, and we claim that in our model, in our system, each particle can have a +1 direct +1, so the spin is pointing upwards, or the spin can have a negative value, which basically we're saying it's a SZ, -1. This is SZ. And it jumps between those two values. In general, we know that it's not true because there are several values in the z direction, and there are several values of the total spin, and there are eigenstates. But for simplicity, we're taking that each particle can have a spin up or down, and the value of the spin up is +1, the value of the spin down is -1. Okay, so this is call it SI. Basically, we're looking only on the Z projection of the spin. Now, the energy, you already know this, that is associated with each value of the spin. The energy is EI, let's call it E, of a specific spin, is simply the SI multiplied by the external field, multiplied by mu, which is related to the Bohr magneton, and the minus sign over here. Okay, now H can be either up or down, so only positive or negative, because everything that we're looking here in this model is only the Z direction. For each spin, there is only one direction. It only can actually go up or down, and the external field can be in the Z direction or minus Z direction. It can be positive or negative. Now, what we see here is that we expect the system to lie in what direction? In the direction of the external field. So if H is positive, S would prefer to be also positive. Why? Because then the total energy becomes smaller. In equilibrium, energy is a minimum. Okay, so this is why we have a minus sign over here. So positive direction of H, a preferred positive direction of S. Negative direction of H, a preferred negative direction of S. Very, very simple. Now, if we would have only a non-interacting particles that won't care about each other, okay, we will have an energy that is minus I goes from 1 to n. We'll have n particles, and we have H mu Si. Okay. So this is a free particle picture. Okay. We can plot it as, well, we have a lattice. It can be one-dimensional lattice, two-dimensional lattice, three-dimensional lattice, four-dimensional lattice, if you can imagine something like this, or five-dimensional lattice, I don't really care. Okay? And on each lattice spacing, we have a spin that points either up or down. This is all we have. Now I'm plotting here a two-dimensional case because it's the simplest, right? But you can plot it in three-dimension, two-dimension, square lattice, triangular lattice, comb lattice, whatever you like. Now, in the non-interacting case, each of the spin here, which is either plus or minus 1, plus 1 or minus 1, don't care about its neighbors whatsoever. And then the total energy is whatever I have this expression that I've written over here. Right? Now, what happens in reality? We know that there are some sort of interactions. Okay? So, since this spin is pointing upwards, its neighbors will also prefer to point upwards. Maybe. Why? Well, because it's in a field. If it's pointing in this direction, it creates some sort of an effective field around it. Then its neighbors, this guy or maybe this guy, will say, well, this spin is going up. I will also prefer to go up because he's affecting me. Somehow there is a magnetic field going up from the spin. Now, those interactions, exactly those interactions that are making this system interesting. Otherwise, it's completely not interesting. We'll see it in a second. How I define those interactions. So I'm saying, let's take S in position R on my lattice. And I will take also S on position R prime on my lattice. Okay. Now, what is what is the contribution of those two spins. Right? Now I'm saying if those two spins are pointing in the same direction, the total energy of the system should go down. Right? Because this is what I said. I prefer to be in the same direction as my neighbor. So I shouldn't care about the sign. They don't care about if it's going up or going down. Right? So if I'm pointing up, my neighbor should prefer to go down. But if I'm going down, my neighbor should also prefer to go down. And those two states should be equal in the energy, right? Because the only thing that the energy should matter is not the global direction, but that they are oriented in the same direction, right? So I'm saying the contribution of interactions, the simplest form for the interactions is a multiplication for two spins. If I'm taking spin r, it's a multiplication to spins, and I will multiply it by some prefactor. We'll call it r minus r prime, j r minus r prime, and j is the magnetic coupling constant. Okay. Now, j is greater than 0, so I should place here a minus term. Why a minus term? J is positive or negative, is positive, can be 1, 2, 3, or 0 if the interaction is 0. And if the two spins are pointing up, the total energy should go down, because this is my preferred state. That all the states or all the spins are pointing in the same direction. Why I'm saying that? Because there is a magnetic field from this spin on that spin and from this spin on that spin. But I shouldn't care if they're pointing up or down. This is why the multiplication. So if SR is up and SR prime is also up, this guy in total is negative. If SR is down and SR prime is also down, this guy is total is also negative. But if one of them is up, the other one is down, okay, then the total magnetization, the contribution of this part is positive, so the energy goes up. Okay? This is not something that I will prefer. This is my simplest interaction. Okay. So, how I write down the total energy of the system. So the total energy of the system is written down, or first of all, let's write the interactions. So the interactions, minus sum of r prime, j r minus r prime, sr prime. I have a minus over here. And the summation here, it's a double summation. So it's a summation over r, and it's a summation over r prime. Okay? I take one spin, and I'm saying, what is the effect of this spin on everybody else? Okay? I'm taking S1, I'm looking on the effect on S2, S3, S4, S5, S6. I'm going over all different positions of the other spins. This is the summation over r prime for a specific r. But now I'm also should take into account not to start only from here, but to start from everybody else. But by doing this double summation, I'm overcounting. By how much? Exactly 2 times. Because when I took this particle, I also took into account the effect of this particle on that particle. Now when I start the counting from this particle now, I again take into account the effect of this particle on that particle. I don't want to overcount, so what I do, I introduce 1/2 over here. Okay. because I don't want to double count, and I don't want to restrict my counting, because I want to take any pair of the spins only once. So now we have this interaction term. Eventually, I can write down the total energy of the system. So first of all, there is mu h, sum of r, s of r. Instead of taking a dummy variable of I, I'm going over r. And there is minus 1/2 a sum of r prime, j r minus r prime, s of r prime. Now you see j of r minus r prime, the magnetic coupling constant, it's not always a constant. It depends on the distance between the two spins. So if the spins are really far away from each other, there should be no effect. So what I expect is that this complex magnetic coupling constant should go to 0 as r minus r prime goes to 0, and it should go to a finite value that I will define when it goes to very close to each other. So I should have an effect on the neighbors, and I don't expect to have any coupling constant, no effect whatsoever on the particles that are far away there in Yossi's office. Okay? Now, the total number of the spins is enormous. It's huge. We're talking about a macroscopic material, so we're talking about 10 to the 23, 24 numbers of spins that we have, and we have to take all of this into account. We have to take some j's. Sometimes for simplicity, people say, well, I would have only effect on the nearest neighbors. We'll have from this guy will effect on this, that, and that spin, and nobody else. It doesn't really matter for our purposes. But it's still something really hard to do now, because we now have to sum over huge number of spins. Okay? And in the next lesson, we will see how exactly we are going to do this. So there are some approximation technique, and we'll try and use it in order to obtain, at least qualitatively, what is happening with a system that the energy is defining like this. And this is for us the Ising model. There are some generalization of this model, like a Potts model and Heisenberg model, etc., but it catches a lot of physics already. This guy, because, well, you haven't done almost anything, spins, interacting, etc., but this is actually very complicated. As I said to you already, it took an enormous effort of Onsager in 44 in order to solve it for 2D and for nearest neighbors. So J of R was 1 for 1, 2, 3, 4 particles and 0 for everybody else, and only then he could actually do something. And even there when H was 0, so you understand how complicated this. For example, Landau, it's, oh, he never admitted that, but he probably haven't managed to solve this. Okay? It's really hard. It looks very simple, but it's hard. Those interactions, this guy over here, it's a headache. So we are going back to this equation, and what we are going to do is to take a trace. So this is E, right? Now what we want to understand, the statistics of this problem. And what we need to calculate in order to do this is to take a trace over this guy. Okay. Now what I mean a trace here, what I mean by trace. So I already told you that, well, if I have an Hamiltonian, I should write here an Hamiltonian, find all the different eigenstates of this Hamiltonian, and take a trace of this big function, this big operator. Now, what are the eigenstates of my Hamiltonian? I already have written you. Those are the different energies. So the eigenstates are the different possible values of all the spins that I have here. So let's take an example. Let's take a look on an example. So let's take 2x2 system. So I have 4 spins in my system, right? So I have this guy, this guy, this guy, and this guy. Okay. And even not 2x2, it's too much. I have a system of 2 spins. Okay. Now, what are all the possible eigenstates and eigenvalues of those spins? In order to write this down, I should go here. Okay. Write instead of S of r and S of r prime the operator SR and the operator SR prime. Take only the z value, which is the spin operator, and I know it should take values 1 or minus 1. Now, I don't want to take this, transform it into an operator form. I'm just saying I will use this form of a summation to write down the summation. What I mean by this, that I'm going to take into account all the possible states in the system. So if I have only 2 spins in the system, it is really easy to show, not to show, but it's really easy to understand, that the eigenstates of the system is the 2 spins are up, the first spin is up, the second spin is down, the first spin is down, the second spin is up, the first spin is down, the second spin is down. Those are all the possible states of the system. There are no other states. Those are the eigenstates. Now, for each state, I should write e to the minus beta e. Okay? So let's write it down. Let's write it down. So for this state, I write down to here e to the minus beta e. So for the 4 different ones. So for this state, it's e to the power minus beta. And inside, instead of e, I'm writing this down. So it is mu h multiplied by plus 1, okay? 2 of them are up. And I have, with a sign of minus, minus j, because there is always j, 1 and 1, there is only one j, right? Because the distance between those 2 spins is constant. Minus j plus 1 multiplied by plus 1. So this is the contribution of this state. The second guy will give us e to the minus beta minus mu h. Here I have the first spin is plus 1, the second spin is minus 1, and here I have minus j multiplied by plus 1 and minus 1. Okay. The third part will be e to the minus beta minus mu h minus 1 plus 1 minus j multiplied, the first one is minus 1, the second one is plus 1. Now, I had also here a summation and here a summation, but the summation was multiplied by term 1/2. So this guy multiplied by this guy, and plus this guy multiplied by this guy. And everything is multiplied by 1/2 over here, so I really don't sum over anything. The third situation is e to the minus beta minus mu h, and I have minus 1 minus j multiplied by minus 1 minus 1. Okay. Close my parenthesis. So this, guys, this factor for this state is e to the power minus beta mu h multiplied by 2 and minus beta, plus, I'm sorry, plus and plus beta j. This guy gives us e to the power of minus beta plus 1 minus 1 is 0, so I don't have this term. I only have minus beta j. This term, again, minus 1 plus 1 is 0, so that I don't have a contribution from the external field. I have only e to the power minus beta j. It's exactly the same as this one. This is the symmetry. If this one is up, this one is down, it's exactly as the Boltzmann factor, this factor, is exactly as is this guy is down and this guy is up. It's only e to the power minus beta j. Third term is e to the power of minus beta mu h multiplied by 2. And here I have minus 1 is plus 1, minus j multiplied by minus beta is plus beta j. Plus beta j. So what we see that z for 2 spins is simply e to the power of 2 beta mu h plus beta j plus e to the minus beta j plus e to the minus beta j, okay, plus e to the minus 2 beta mu h plus beta j. Okay, so it's a not so nice expression. It has 3 terms for 2 spins. Now let's think how the summation would look like for 10 spins. It's going to be nasty. Why? Because we should have 1 spin up, 1 spin up, third spin up, down, down, down. So I should count on over different situations of the spins. Each of those situations is an eigenstate. Okay? So for 2 spins, it's really easy. Up, 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 down, down, up, down, down. For 3 spins, it becomes more complicated. Okay? And in general, how many eigenstates I would have? 2 to the power of n. Okay? So what I'm getting is that these summations are becoming harder and harder. So for n spins, there are 2 to the power of n eigenstates that I have to count. And for each eigenstate, I have to count its specific Boltzmann factor. And then I have to sum everybody up, and only then I can start to understand something. I can take a derivative of it, etc., etc. So this is the partition function. Then I have to do something to study. But this is a huge sum. And it's really, really complicated because I have to take everything into account. More importantly, so here I was using a single j. J was constant. But in general, j is a function of r minus r prime, right? The spatial distance between the 2 spins. The farther they are apart, the smaller j will become. The closer they together, the larger j becomes. Usually j is between 1 and 0, okay, or multiplied by something. But you see that this becomes a problem. This becomes a really, really hard problem. Now let's take, why? Because of the interactions. I will show you that actually it's a simple problem when there are no interactions, and it's a very hard problem when there are interactions. Okay, so first of all, let's see what happens to the Ising model when there are no interactions in the system. Okay? This is the trivial case. What do we expect in the system to appear? We expect that the system will behave in a paramagnetic way, paramagnetic fashion. Okay? So no interactions. So for no interactions, E is simply minus mu h sum of r s of r. Okay. Now write z as a trace of e to the minus beta e. It equals trace of e to the power of beta mu h sum of r s of r. Now this guy, I know that this is a trace of what? Of e to the power by beta mu h s of 1 multiplied of e to the beta mu h s of 2 multiplied by e to the beta mu h s of 3 and etc. 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 Okay. Now I write it down as a trace of multiplication over r of e to the beta mu h s of r. Because it's just a simple multiplication. Now, what I'm taking here, what is a trace? A trace, we can write it down explicitly. A trace is a sum over S1 equals 0, minus 1 and 1. S2 equals minus 1 and 1. S3 equals minus 1 and 1, etc., etc., etc. So the trace is just a simple summation over all possible values of each of the spins. Now, I already got here the factorization that I'm always looking for when there are no interactions. You see, when there are no interactions, I always look for factorization in my partition function, because this is the way to sum over everything. Okay, so this is the sum over all different situations. Here I have a simple multiplication over r, e to the beta mu h s of r. Now the usual trick that I do, I'm saying I can, so here I have a summation and then a multiplication. Now since they are all independent of each other, what I can do, I can first sum and then multiply. I can first sum everything and then I will multiply. Okay, so what I'm actually doing, that it's pi over r, and here I will have this summation of SR equals 1 and minus 1 of e to the power of beta mu h s of r. How I can do it? I can multiply everybody, and then to start, first of all, sum over the first one. So it's the first one at this state plus multiplied by everybody. Then the first one and the second state multiplied by everybody. I take everybody out of the parentheses and I get just only the summation. So this operator of the summation for a single one and the multiplication, they're commutative. Okay, so what is written over here is pi over r, a trace over e to the beta mu h s of r. Okay? I only need to count all the states of a single spin, and a single spin can be either up or down. Okay, and what is this trace of e to the beta mu h of s of r? It is a summation. Pi of r is simply e to the beta mu h multiplied by plus 1 plus e to the beta mu h multiplied by minus 1. I count all the possible states that I have for a single spin. Now, you see, it does not depend on r. It's everything, it's the same for everybody. This is the factorization that I was always talking to you about. So what we got that z equals multiplication over r. And this guy I can write down as 2 times cosine, hyperbolic cosine, so cosh, of beta mu h. Okay. Now, how many spins I have in the system? So this is in order to know how many to multiply. I have exactly n spins. So this multiplication is simply 2 to the power of 2 cosine, hyperbolic cosine of beta mu h to the power n. Okay. So we managed to solve something. How it helps us. What we need to compute. So we know for the non-interacting case, what is the partition function? Now, what is our observable? Our observable was the net magnetization. When I'm saying the net magnetization, I already told you that magnetization is actually fluctuating as a function of time. Those fluctuations are small because each spin we expected it to go up or down, up or down. So when I'm saying m, which is simply equals to sum of r mu s of r, okay? The thing that I want to compute is not m, is the average m, which is the average over the sum. Now the average over the sum is simply mu, because mu is constant, mu sum over all the r's, and I have the average of SR for each of them. So what I need to compute is, this is my observable, the average m, right? Which is just the sum of the averages of all different particles, or different spins. Now, I already know how to compute this guy. Why do you know how to compute it? Well, because I have the partition function. And everything that it's related to averages, first moment, second moment, I don't care. I can always compute from z, from the partition function. This is why it's so important. This is why I actually care about computing it. Otherwise, why should I do this? Now, let's see what is average m. What is average m? So, we know the average m is m. What is m? So it's sum over r mu s of r multiplied by the probability of having this specific magnetization. So let's take a specific state, okay? So for example, if we have two systems, what is the magnetization if one of them is up and the second one is up? So we're saying here is mu multiplied by 1 plus mu multiplied by 2. So it's 2 mu multiplied by the Boltzmann factor of this state. What is the Boltzmann factor? Is e to the power of minus beta e. Okay? Now this is the value of the magnetization, this guy, multiplied by the probability of being in this magnetization. What is the probability? Divided everything by z. Now this is the probability of the magnetization to be in a specific state. Now we have to count over all possible states. So should we have trace over here? Trace or just summation over, when I'm writing trace, I'm meaning a summation over all possible eigenstates of the system. Okay? All possible states of the system. Right? So this is what we have here. This is what we need to compute. This guy, the trace of this, z we already know. Z we already know. Okay? And so we need to take a trace or to take a sum over everything. Now, if z is inside, z is not dependent on the trace, it's already a summation. It's simply 1 over z, a trace of sum of r mu s of r, right, multiplied by e to the power minus beta e. But what is e? E, we're using the no interaction condition. This is E. Okay? So let's use this E. Let's introduce it over here. The same way as we introduced it before in order to calculate the partition function. So what we have, that average m equals 1 over z trace over a sum over r mu s of r multiplied by e to the power of minus beta e, so it's minus minus beta mu h sum of r s of r. Right? This is the function that we have. We have absolutely no interactions. Now, look at this guy. This is the usual technique of the partition function. So we have something multiplied by the Boltzmann factor. Now, this guy over here is exactly, if you introduce this guy multiplied by this guy. Right? This is a sum mu multiplied by SR, and here I have mu, a sum over SR. So only this guy, this multiplication, I can write down as 1 over z. This trace is basically a summation for me. I just sum over all the states. And here I have d of e to the power beta h sum of r mu s of r by d beta h. Right? If I take the derivative of this term with respect to beta h, okay, I will get exponent of beta h sum of r mu s r, this is what I have here, multiplied by whatever is multiplied by beta h. This is this big sum. Okay? This guy. Okay. Now I'm doing the following. So this is a trace of a derivative. But the trace is with respect to what? To all different. It's just a summation. It's a finite summation. It's a big summation. I sum over all the possible states, but it's a finite sum. And here I have a derivative. So I can take the derivative out of the sum. Z is equal 1 over, not Z, is equals to 1 over Z d to d beta h, and here I have a trace over e to the power of beta h sum of r mu s of r. Remember, the trace is just a thing for me. It's just a big sum. So instead of writing a sum over SR and all over different R's, I'm just writing the trace over here. It's just a summation. This is why I can take my derivative out. This is always what we have been doing before for the partition function. We wanted to compute some average. We would describe this average as a derivative of whatever is left inside. But what is this trace? It's just the partition function, right? Right? So this is it. This is the trace. Here it goes. This. So what we have here is that M average is 1 over Z d to the d beta h of Z. Okay? This is simply d to the d beta h of a log of Z. So in order to compute the magnetization, we need to take the derivative with respect to beta h of this guy over here. Okay? As simple as that. So it's a little bit cumbersome over here, but it's the same technique that we already seen before for all different statistics. Right? And it's always the same trick. You need to represent your average as some sort of a derivative of the logarithm, right? Of the logarithm or some function of the partition function. Okay. Let's write it down already what we have. So for the non-interaction fixture, it's d to the d beta h, and log of Z is log of, this is our Z. What we have here, it's 2 hyperbolic cosine of beta, mu, and h. And this is to the power of n, and I close my parentheses. Right? Okay, so first of all, let's take n out of the picture. So M average is equals to n d beta h of what we have left inside of log of the 2 log of 2 plus log of what? Of a cosine hyperbolic beta, mu, and h. Okay? This is what we have. Now, the derivative of this guy just disappears, so we don't care about this. And we have n. And now we're taking the derivative with respect to beta h of the log of a cosine. So it's n divided by 1 over cosine of beta mu h multiplied by a hyperbolic sign, because the derivative of the cosine, hyperbolic cosine, is hyperbolic sine. So it's, you know what a hyperbolic cosine is, right? Yeah, okay. So, write it down over here. So it's a hyperbolic sine of beta mu h multiplied by, I have taken the derivative with respect to beta h, so it's just multiplied by mu. Okay, so what we get over here is that m average is simply n multiplied by mu multiplied by hyperbolic tangents of beta mu h. Beta mu h. Okay? Not so bad.
Should there be a minus sign in the derivation?
No, it's hyperbolic sign. Okay, so I'll just remind you, it's over here.
There is no minus.
There is no minus. There is no minus because cosine hyperbolic cosine of x, e to the power x plus e to the minus x divided by 2. When you take the derivative, it gets q, so d to dx of cosine hyperbolic of x is e to the x minus e to the minus x divided by 2, and it's just a hyperbolic sine of x. Okay? So there is no minus sign. No minus sign over here. This is a very nice result because you see, since we've got a factorization, we always expect the net result to be what? A sum over averages, right? So you see what I have written over here? The average m that we have gotten over here is n multiplied by mu multiplied by tangents hyperbolic beta mu h. Now, what we already know is that m equals to mu multiplied by the sum of r s of r. Now, in the case when they are non-interacting, I don't care. So this spin, the average value of this spin, and the average value of that spin, they should be exactly the same. They are not interacting particles. They're interacting with the field. They do not care about each other. So for the non-interacting picture, I know that I should get that the average m from this perspective is mu multiplied by n multiplied by SR, or just S average, which is, what is S average? Is the average value of a spin. For each spin, there is some specific average value. The total magnetization is the average value of the spin multiplied by the Bohr magneton, by mu, multiplied by what? The total number of the particles what we have. Now what we have gotten over here is this part. Okay? Now what we have obtained is that m equals to mu and hyperbolic tangents of beta mu h. Okay. Now, first of all, we managed to compute the total magnetization. Moreover, since we had no interactions whatsoever, we managed to compute the average value of S. S average value equals to hyperbolic tangents of beta mu h. Now, for the non-interacting picture, I could either study the average value of S or either study the average value of m. I don't really care because there is simply a constant that multiplies them both. Okay. Now, the moment I have this result, I can go and see, well, I expect a paramagnetic behavior. Would I get it? Yes or no? So let's see what's going on with the average value of a spin. Okay, so this is H, this is S. And hyperbolic tangents, doesn't matter, look simply like this. There is only one single curve, and it crosses 0. So for exactly h equals 0, the average spin is 0. Okay? So what I would have in a system, I won't care where to point. I can point this direction, that direction. On average, I would point anywhere. And this means that the total magnetization for h equals 0 is also 0. So what we're getting a paramagnetic behavior. And this is what we have claimed. There is a symmetry in the system. The spins do not care about each other. They don't care about any direction because there are no external field. On average, I won't have any magnetization. I will have some sort of small fluctuations, but those fluctuations are small. Okay. So this is what we're getting from the Ising model, which is a representation of a magnetic system, and we're neglecting interactions completely. Okay. Now, our next step is going to be to take those interactions into account and see where it gets us. Right? So, yes, we solved the easy problem. Well, maybe it wasn't so easy for you, but it's actually easy. Okay? Because we used already all the techniques that we know, and there were not something very special that we had to do. We managed to do factorization, and then we represented everything as some sort of a derivative. Fine. Let's try and do this again when we have to take into account the effect of the field, of mutual field on each other. Then when we are taking into account the interactions between the two particles. So what I'm going to do now is to perform the first attempt into solving this Ising model in general, but I won't be solving it exactly. I want to introduce an approximation technique which is very, very important and useful in physics, and it's called the mean field approximation. What I mean by this, so let's think that I have a lot of particles, a lot of spins in the system. Now, I know if there is no interaction, the spins don't care about each other, and they only care about the external field. Okay? They only care about the external field. So when I'm looking on one single particle, if it's going up or going down, it's completely, for the non-interaction picture, it's completely dependent on what is the external field for the system. Now, what happens if there are interactions? So there should be some sort of a competition between the external field and the local field of its neighbors, or all the other particles that are actually affecting it. Now, the idea of the mean field says the following. There is some sort of a mean value for all the spins. This mean value not exactly is given by the hyperbolic tangents, but there is a mean value for each of the spins, right? So each spin, it's on average pointing somewhere, and it's also fluctuating around this direction. Now, if all the other spins were just pointing in this mean direction, I would have a general net effect on this particle, that is going to be constant because I'm taking into account only the mean values of its neighbors. Okay? So this is approximation. Why it's an approximation? Because I have thrown out the actual values of the spin of the other spins and replace them by the average value of the spin. Okay? But by doing so, I effectively created an external field which is constant that is applied to the spin due to its neighbors. So the mean field approximation is stating the following. There is very complicated effects, mutual effects. Now instead of taking them, all of them into account, let's assume that all the particles are equal, or the spins of all the different spins are exactly equal to what? To their average value. By doing so, we will create non-interacting particles where each of the particles is affected by the external field and the constant local field due to its neighbors. Now, since everything looks the same, so I don't care, so the average value of everybody is independent of their position, okay? So this constant field is going to be exactly the same for this particle, and this particle, and this particle, and this particle. So what's happening? I'm taking interactions, replace them for each particle by an effective field, and then I said, well, this field is exactly the same for everybody, so I'm going back to the non-interacting picture. By doing so, I would be able to solve everything. Let's see how it happens in the math on the board. But the idea is, let's replace the effect of a particle but by its mean effect. This is why it's called mean field approximation. Instead of taking the real field of each spin, I'm taking its only mean field. Mean, I mean average. Okay. So in order to perform this, I would like to write down two approximations. So first of all, let's look what is S of R and S of R prime. What exactly are they? So we know, let's write down this as S average plus SR minus S average. Okay. So I haven't done anything wrong, and the same I will do for SR prime. I write it down as S average plus, this is, I don't know what S average is, so I know what S average is for the non-interacting picture. I don't really know for the interaction picture what is S average. Interactions included. See, and those are the interaction terms, the multiplication of one spin by the other. So S plus SR prime minus average S. Okay, so the next step is to define delta of S of R is the value of S of R minus S average. Okay, now let's open up those parentheses. So what we get that SR prime equals to S average multiplied by S average. So it's S average squared plus S average multiplied by delta S of R. Delta SR prime. Right? Plus S average multiplied by delta S of R. Okay? And then there is the third term, plus delta S of R multiplied by delta S of R prime. So delta S of R multiplied by delta S of R prime. The mean field approximation is saying the following. Oh, this is something. This is something. This is also something. So this is the first order. This is zero order. This is first order. This is first order in S of R. And this is the second order in S of R, delta S of R. I shouldn't care about those small fluctuations. Let's kill them. Right? We're neglecting them. Okay. By doing so, we can actually calculate our interaction term. Because we're saying, instead of using this form, we're going to use this form for the interaction part. Okay. So let's see how it works. Now, 1/2 beta, a sum of r prime, j of r minus r prime, multiplied by sr prime. So this is the interaction term. The interaction. We need to do something about this term, and what I'm going to do is actually use this representation of sr prime in order to make here everything much more simpler. Instead of having two sums, I will have only one single sum. Okay. So what is equals to? It's equals to 1/2 beta. And here I have the following. Sum of r prime, j of r minus r prime. And here I'm using this representation of sr prime. Okay, so I'm going to use this guy. Okay, so what I have? So first of all, I have s average squared plus average s multiplied by SR minus S average, and I also have plus SR prime plus average S multiplied by S of R minus average S. Yes, and I will close my parenthesis. Okay. Now, what can I do? I can restate it as 1/2 over beta sum of r prime, j over r minus r prime. Here I have s squared plus minus s squared minus s squared. Okay, so I have minus in total s squared, and I have plus s of r plus s of r prime. Remember, I don't know what this average s is. I'm assuming that there is some average value. I don't know it, and I should have understand what this value is from the final answer. All right. What is our next step? We still have to perform these big summations, right? We have sum over r, sum over r prime. Let's do it step by step. So first of all, we can separate this into three sums, right? This is a sum for this guy. This is the first sum. This would be the second sum. This is going to be the third sum. But look, the second sum and the third sum, let's write it down. So we have the first sum is a sum of r prime, j of r minus r prime multiplied by minus s average squared. The second sum is sum of r prime, j over r minus r prime multiplied by s average sr. And the third term is sum of r prime, j of r minus r prime multiplied by sr prime. Okay, we need to calculate those three sums, but look on this guy. Do I care if I count first over r or over r prime? This guy is equals exactly to a sum of r prime, sum of r, j of r minus r prime, average s of r. So this guy, I don't care if I count first over r, afterwards over r prime. It's just a dummy variable, so it's exactly equals to the second term. So the third sum and the second sum is exactly the same, so I'm only left with the first and the second sums to count. Now, here what I have, here I'm saying I could do this as, let's take s average squared out with a minus sum. I have left with r prime, j over r minus r prime. Now those are interactions and they are constant. Somebody should tell us what they are. But I know that a summation over r prime, so it's a sum of r, and here I have just simply j. What is j? J is a sum over r prime of j of r minus r prime. Now I'm saying it's should dependent on the r, right? But the lattice is invariant, so I don't care if I'm looking if the interaction of this guy with everybody else is the same as the interactions of the other guy with everybody else. Okay. I state that they are independent of r. Now, I left with that 1 simply equals minus s squared, sum of r over j. So it's j, the sum over r. Of what? Of 1. How many particles do I have? How many spins? N spins. So I obtained that the first sum is minus s squared j multiplied by n. Okay, so this is the first step. Now I only left with computing this guy over here. Okay, so the second term is sum of r prime, j of r minus r prime of s of r equals to sum of r, so let's take s out, sum of r, sum of s of r, right? And here I have a sum of r prime, j over r minus r prime. But I know what is the sum of r prime, j r minus r prime. It's simply j. So I have here s, sum of r, s of r, multiplied by j. And that's simply s multiplied by j, the sum of r, s of r. Okay, so the third one is then, it goes 2. This is 1. And the third one, we know that the third one equals 2, which means that the third sum is equals to s, j, sum of r, s of r. Great. Okay, now we're in a position to actually do something, because what is E? E is equals to minus beta mu h, minus mu h sum of r s of r minus 1/2 sum of r prime j r minus r prime s of r prime. Okay, and we can now state that minus beta e equals, so first of all let's multiply everything by beta, so it's minus mu h beta mu h sum of r s of r. And instead of this guy, what I do, I use the 1, 2, 3 terms, right? It is plus beta multiplied by 1/2 multiplied by the first. What is the first? It's this guy. So it's minus s average squared j of n, okay, plus beta multiplied by 1/2 multiplied by 2, because 3 is equals to 2, and here we have average s sum of r average s j sum of r s of r. This is our e to the minus beta e. Okay, so z, which is equals to trace e to the power e minus beta e, equals to trace e. So this guy is constant, let's take him out, minus beta over 2 s average squared j n multiplied by e to the power of, let's take everything into account, beta, and here we have mu h plus average s j multiplied by a sum of r s of r. let's take a closer look. What is Z? This is not dependent on the different states of the spins. We can take it out. It's simply e to the power minus beta divided by 2 s squared j of n multiplied by trace of e to the power beta mu h plus average s j sum of r s of r. What is this? There are no interactions between different spins. Right? It's just beta, some effective field, multiplied by the sum over all the spins of the field. There are no interactions between the spins over here. This is what have we managed to do. We said, let's take into account only the effective field by its neighbors. I don't know what this field is, right? So because I don't know what average S is, but I know that it's not interacting right now. This guy, we know how to write it. What is this guy is? It is 2 hyperbolic cosine of whatever is inside, which is beta mu h plus average s j, right, to the power of n. Where we got it from? From the non-interacting picture. What is the field? This is the field, not just mu h. It's mu h plus sj. Everything here should be multiplied by minus beta over 2 s squared j n. We don't care about a constant prefactor. It's just a normalization for us. Is equals z. Hooray, hooray, we managed to solve it. Now, what is the average magnetization? It's the same as d to d beta h of log of z. It stays the same. I don't really care what z is. This formula is always correct. So what I'm getting that average m equals to what? Equals to mu n hyperbolic tangents of the field that I have inside. Instead of beta mu h, I have beta mu h plus j average s. This is my average m. But I know if I have a non-interacting picture, I should have m equals to mu n average s. Because they are all constant. This gives me those two equations. Give me the solution for what is the average s in this system. So from those two equations, I should have that average s equals hyperbolic tangents of beta mu h plus js. This is a non-trivial equation, right? We cannot just simply solve it. But this is a solution of the s. This is what is written here. Let's write it again. Average s is a hyperbolic tangents of beta mu h plus j of s. Now, what do we expect? What do we want to obtain? We want to obtain a spontaneous magnetization. I will take another 3 minutes of your time, I'm sorry. What is the spontaneous magnetization? Now, when spontaneous magnetization appears, when the external field is 0. Okay, so for H equals 0, we should find that average S equals to hyperbolic tangents of beta J S. So let's write down as a function of S, let's write down over here. Let's have two plots. First of all, what is the derivative of tangents beta J of S with respect to S? D to ds average. I know that it's for S equals to 0, it's simply beta J. Okay, so the slope of this hyperbolic tangents when S is going to 0 is beta J. Now I want to make two distinctions. This is tangents a parabolic of beta J average S. This is average S. So for the case when beta J is smaller than 1, and I plot the hyperbolic tangents, it looks like this. Now, if on top of this, I will plot a linear function like S, I notice this is just S. Okay, so S equals S. The slope of this guy is 1. The slope of this guy is beta J, and it's smaller than 1. So I have only one intersection point. This intersection point is, so tangents hyperbolic of beta J S equals S only for S equals 0. Okay, so this is the first case. The second case is when beta J is greater than 1. So again, I will draw my hyperbolic tangents hyperbolic beta J of S as a function of S. It looks the same, it's just the slope that it's different. Okay. And on top of this, I plot again this linear function, but here, because this slope is higher than 1, I'm going to have two solutions. Here, 3. Here, and here. This is S. So, hyperbolic tangents of beta J average S equals average S for 3 different points. This is the non-trivial solution. This guy and this guy. And look, we have two of them. One is positive. So here, S0 greater than 0. Here is minus S0 smaller than 0. And this is our exact spontaneous magnetization. Because what we have managed to do, we managed to find a solution that average S is non-zero, and then the total magnetization is also non-zero because it's mu multiplied by n multiplied by average S. Right? So what we have obtained is that for a specific value of beta J equals 1, there is a transition from paramagnetic behavior to ferromagnetic behavior. So beta j smaller than 1, it's paramagnetic. Average m equals mu n average s equals 0. And beta j greater than 1, it's ferromagnetic. M equals mu n S0. Plus minus two solutions, not only one. We obtain something really strange. We obtain something that it could be plus over here, but also this solution is possible. And this is ferromagnetic. And we will see that exactly at beta j equals 1, it defines us the transition point, because it means that j divided by k Boltzmann equals Tc. We also found our critical temperature, or Curie temperature, which is a transition from paramagnetic to ferromagnetic. And we haven't changed the interactions. The only thing that we changed is the temperature. The interaction stayed the same. It's that here they don't matter, and here they matter a lot. And there is a very tiny point of transitions between those two. We'll continue next week.